Hello everyone. We are going to take some notes tonight on calorimetry. So we know a little bit about calorimetry already because of the lab we did with the heat of solution lab that we finished up earlier. But now we're going to sort of formalize that a little bit and expand on it, so we'll learn a little bit more about this idea. All right, so we'll start with the definition. Calorimetry is the accurate and precise measurement of heat changes in a physical or chemical process. We're going to, of course, be focusing on the chemical processes, but this is true for physical processes as well. So that's your definition of calorimetry. All right. So, and in order to measure those precise, how do we put it? Precise and accurate measurements of heat change, you need a device, and the device is called a calorimeter. This is what we used in our heat of solution lab earlier. Now for us, our calorimeter was two styrofoam cups, one inside the other, so that the sides and bottom were insulated, but of course the top of our calorimeter was open to the atmosphere, and we had a thermometer in there to measure the change in temperature, and we equated the change in temperature to changes in heat. All right. So in general, so that was our specific version. And in general, a calorimeter is an insulated device, like our styrofoam cups, where you measure absorption or release of heat in a chemical or physical process. All right. And so, so that's what a calorimeter is. Now, for systems or reactions or processes where pressure is constant, which was the case yesterday when we had our calorimeter sitting on the bench top. The atmospheric pressure, the calorimeter was open to the atmosphere, and so the pressure around our calorimeter was constant, so we had a system with constant pressure. In that case, the heat content of our reaction is the same as a property called enthalpy. All right? This is only true in this constant pressure situation that we will have for pretty much all the reactions that we do. Where you have constant pressure, that means the heat content of your reaction is called enthalpy, or it's the same as enthalpy. The abbreviation for enthalpy is H, capital H. And so a change in heat content at a constant pressure is called the change in enthalpy, delta H. All right, just like delta T was the change in temperature, delta H is the change in enthalpy. And in this constant pressure system, delta H, which is the change in enthalpy, is the same as Q. So this is really, we're just really adding a new name to something that we already learned about. We learned about Q and how Q equals C times M times delta T, or Q equals the specific heat times the mass times the change in temperature. And now I'm telling you there's this new label for the same thing. We're now going to call it delta H. If the pressure is constant, if it's a constant pressure system, then delta H equals Q. All right? So it's just a little bit of an addition to our current terminology. All right, well, we're going to use that in the next piece here, in the idea of thermochemical equations. So we're very familiar with chemical equations. We write reactions, or have written equations for chemical reactions many, many times. Now we're going to add a new component to our chemical reaction. We're going to add a heat component or a thermal component to our reactions. And we'll change the name. Instead of just a chemical equation, it's now will be called a thermochemical equation. So, definition: a thermochemical equation expresses the heat needed or released in a chemical reaction. Here is an example of a thermochemical equation for an exothermic reaction. So we have calcium oxide and water reacting to produce calcium hydroxide and some energy, some heat. So in other words, if you mix calcium oxide and water together, it produces some heat. And so we have our two reactants, and we have our arrow. Here's our product. But look what we've added to the product side of the reaction. We've added this number, 65.2 kilojoules. What this tells us is that heat in the form of kilojoules, all right, is a product in this reaction. It's given off. It's being produced. Heat is being produced. This is an exothermic reaction. Heat is being given off. All right, and so we show that by putting a heat term on the right side of this equation, and in this particular case, the heat term is 65.2 kilojoules are being produced in this chemical reaction. Now, with that, we can actually write that a different way. The same equation, but in a slightly different way. You'll see we still have our two reactants the same, and the product, calcium hydroxide, is written the same. But here, in this instance, we're writing the heat term as a delta H. All right, so here delta H equals negative 65.2 kilojoules. All right, well, up here, I'm telling you these are the same reactions. They are. But up here I showed the 65.2 as a positive number, and down here I'm showing it as a negative number. That might seem a little confusing, but let's work it out. In this first example, the heat term is included within the reaction. Do you see how there's the plus sign and then you've got your heat term? So the heat term is just like another product or reactant. It's shown as a term inside the reaction. In this lower situation, the heat term is pulled out separately. You can see there's not a plus sign between here, the product, and here, the delta H term. All right, so it's just kind of a difference in or personal preference almost. These two things are equivalent ways of expressing. You can choose to use either one. But when you show the heat term as not part of your chemical reaction, which is the way we've got it here in the bottom, there's not a plus sign connecting delta H to the rest of the reaction. In that case, then you need a negative or a positive sign to tell you whether your reaction is endothermic or exothermic. In this earlier example up here, we can see that the heat term is part of the reaction because of this plus sign that holds things together. And we're showing the heat term on the product side, which means heat is a product or heat is being produced, which means it's exothermic. Down here, we wouldn't know that unless we had a negative sign in front of this 65.2 term to tell us that it's an exothermic reaction. Remember, if delta H, well, if the heat term is negative by convention, we say that means the reaction is exothermic. And so here, if delta H is negative, it means it's an exothermic reaction. If delta H is positive, it means it's an endothermic reaction. All right, you only need to worry about the negative or positive sign if you use this second example as of a way to write your thermochemical equation. If you're writing your thermochemical equation like this first example, you always show the heat as a positive number. And I'll show you an example of an endothermic reaction in a second. All right. So once we know delta H, and we can see that this heat term is just part of our balanced chemical reaction, we can then calculate amounts of heat that are gained or lost. I'll show you an example of that right after this next slide. All right, so here is an example of an endothermic reaction. The previous example was exothermic. Here's water decomposing to H2 and O2. All right, and notice that we've seen this reaction many times before, but now I've added a heat term to it. However, notice that the heat term is on the left side. It's on the reactants side of the equation, and that means that we can treat heat as if it were a reactant. That means it gets used up. That's how you know this is an endothermic reaction, because it's taking in or using up heat. All right? And once again, you notice there's not a positive or negative sign in front of this term, but if we chose to write that equation with the delta H terminology and you put it over to the side rather than having your heat term inside the reaction itself, but instead you show it off to the side like this, now we show that 483 kilojoules is a positive number. You notice there's no negative sign in front of it like on the previous reaction. So delta H is now a positive number, and delta H is positive. That means the reaction is endothermic. You can tell that from either of these examples. You can tell it from this bottom example because delta H is a positive number, and you can tell that it's an endothermic reaction in the upper example because the heat term is on the left side as a reactant. All right, you see the two differences there? So heat term on the left or delta H positive means endothermic reaction. Heat term on the right or delta H negative would be reaction is exothermic. All right, let's look at an example of the kinds of calculations that we can do. All right, and there's so gasohol is a gas substitute that some vehicles have been designed to burn. It's gasoline and ethanol mixed together. And so here's ethanol, C2H5OH, And gasohol burns in oxygen to produce carbon dioxide gas and water vapor. Actually, I should correct that. Ethanol burns to produce carbon dioxide and water. That's the reaction we're going to focus on. All right, so if I give you a balanced equation for this, you can calculate how much heat is released in this exothermic reaction when you burn a certain amount of ethanol. So here is our balanced chemical reaction. We have ethanol, C2H5OH, it's a liquid, and 3 oxygen molecules will combine to produce 2 carbon dioxide gas molecules and 3 water molecules, plus a bunch of energy. Now notice our heat term is on the right side of the equation as a product. So that tells you that this heat is being generated. It's a product. That means it's exothermic. Heat is being given off in this reaction. The other way we could have written this, I don't think I have the example. Yeah, the other way we could have written this would have been to show delta H, use the delta H terminology and say the reaction is here and delta H equals negative 1,235 kilojoules. I find it generally easier to use the heat term as a reactant or a product, and it's a little bit easier to keep track of. But again, it's kind of a personal preference thing. So, just as a reminder, you can tell this is an exothermic reaction because the heat term is over here on the right side. Okay, so we are going to, the calculation we're going to try to do is how much heat will be generated, how much heat is released when 12.5 grams of ethanol, this stuff, is burned. All right, I sort of rewrote the equation up here so we could see it again. Here's how we set this up. You're going to think back to your stoichiometry days and mole ratios, and if you get that in your head, I think that will help. All right, here's how you do that calculation. You take 12.5 grams of ethanol because that's what they gave us right here. Yes, 12.5 grams of ethanol. And we use the molar mass of ethanol, 46 grams per mole. I turned it over so that the grams will cross out. All right, this step converts our grams of ethanol to moles of ethanol. And now look at this term right here. I wrote negative 1,235 kilojoules per 1 mole of C2H5OH. How did I get that? Well, I used stoichiometry and I looked at our balanced equation. For every 1 mole of ethanol, since there's a 1 in front of this here, the coefficient is 1 in front of ethanol. For every mole of C2H5OH, we get 1,235 kilojoules. And I wrote this as a negative number because the kilojoules are being given off. Heat is being given off. So there are 1,235 kilojoules of heat given off or released for every 1 mole of ethanol that's burned. You could have made other, I'm going to go ahead and call these mole ratios, even though they include a heat term. They're very much like a mole ratio, and you could have put together different mole ratios if we had been given a different starting point. For example, if the problem had said how much heat is released if 10 moles of oxygen are burned, you could then make a mole ratio that connected the kilojoules of heat to the 3 moles of oxygen. 1,235 kilojoules of heat are released for every 3 moles of oxygen that are burned. You see the connection? This is just like a mole ratio in stoichiometry. So that's where this term came from. So we have this step converted grams to moles. This converts moles of ethanol into kilojoules of heat. I'm showing it as a negative because heat's being given off, and when you do the math, you get negative 336 kilojoules. So that means 336 kilojoules of heat are released, that should be are released when you burn 12.5 grams of ethanol. All right, and the negative value here tells you that the heat is being given off. All right, so take-home message here, we're going to add a heat term to our chemical equation to make it a thermochemical equation. The heat term is treated just like the compounds in a chemical equation, so you can make what looks just like a mole ratio that includes your heat term, and you can do calculations with it. We'll see lots of examples of this in the worksheet that we're going to tackle tomorrow. All right, that's it.